These magnets are attracted to each other. Well, these things aren't. They're pulled together by the electromagnetic force. If I add some energy, like shaking them around, I can overcome these forces and they pull apart. Well, things aren't so different in chemistry. If I heat particles, making them move around fast, I can break the forces between them too. I'm Matt Queen, and this is Crystalline Solids. The water molecules in an ice cube are held together tightly. But just like all substances, if we heat them up enough, they form a liquid. The temperature at which a substance melts gives us an indication of how strongly its particles are held together. Let's explore this using some simple experiments to gain insights into the properties of different types of crystalline solids, which have particles that are arranged in a definite repeating pattern. First, let's consider two compounds, sugar and dry ice. Dry ice is solid carbon dioxide. It sublimes, goes directly from solid to gas at negative 79 degrees Celsius. You can melt table sugar on your kitchen stove. When I do this on a hot plate in the lab, sucrose melts at 185 degrees Celsius. It also breaks down into simpler sugars. It undergoes caramelization, which is useful in cooking. CO2 and C12H22O11 are molecular compounds. The temperatures at which they change from solid reflect the relative strengths of their intermolecular forces. But what if we take a different kind of crystalline solid, like table salt, and do the same thing? Well, melting salt is much harder. You won't be able to do this at home. Using a crucible and extra large burners, I can do this in the lab. Sodium chloride melts at 801 degrees Celsius. And look, molten sodium chloride conducts electricity, dramatically demonstrating that it's ionic. Sodium chloride is an ionic compound. It has a very high melting point, simply because it is much harder to break ionic bonds than it is to overcome intermolecular forces. Metals are a third type of crystalline solid. Metals generally have very high melting points. Most are extremely high, but mercury melts at negative 39 degrees Celsius. This is heavy. Metallic solids are good conductors of heat and electricity due to their mobile sea of electrons surrounding their atomic cores. How about a covalent network solid, something like diamond? Would that melt? Atoms in covalent network solids are held together by, well, a network of covalent bonds. These covalent bonds are very strong. So if diamond does melt, it is likely at a very, very high temperature. I asked my colleagues if I could try and melt their wedding rings with a blowtorch. Nobody offered. I settled for a web search and found that diamond melts at above 4,000 degrees Celsius. The flame in a blowtorch is only 2,000 degrees Celsius. Good thing I didn't try. So, it turns out the forces between particles exert a massive influence on how they behave, particularly how they change physically when heated. And there you have it.